Welcome to Olympiad Math for Year 5. This is Lesson 8, we'll learn Number Puzzles Part 1. In this lesson, we will learn solving methods and common breakthrough techniques for horizontal and vertical arithmetic puzzles. Number puzzles refer to a type of interesting mathematical problem that revolves around numbers, such as inserting operation symbols, cryptorhythms, and arithmetic puzzles. When working on these problems, many students tend to use a trial and error approach, that is, trying out a few possibilities in search of the correct answer. This is one way to solve the problem. However, if we can dig deeper into the underlying logic and identify the key breakthrough points, it will be greatly beneficial for developing our analytical and reasoning abilities. Example 1. Insert appropriate operation symbols, plus, minus, times, divide, or parentheses, between the 5 fives below to make the equation true. Since there are relatively few fives, we can work backward, starting from the final result and reasoning in reverse. If a plus sign is placed before the last 5, we get the following expression. In this case, we only need to make the first 4 fives equal 5, and the equation will hold. Continuing to work backward and applying the same idea. Now the task becomes making the first 3 fives equal 0. This is quite easy to achieve, because 5 minus 5 equals 0, and 0 times or divided by 5 is 0. So, valid expressions include these three. If a minus sign is placed before the last 5, this means the first 4 fives must equal 15. Reasoning step by step, we find the following expression valid. If a times or divide sign is placed before the last 5, we still use backward reasoning and arrive at two expressions. Using brute force trial and error can be blind and inefficient, and it often leads to overlooking potential solutions. The right approach is to reason backward from the result, to trace the effect back to its cause, applying reverse deduction to gradually reconstruct the solution. Example 2. Insert appropriate operation symbols, plus, minus, times, divide, or parentheses, between the 14/8 below to make the equation true. If we try to use backward reasoning for this problem, it becomes very cumbersome due to the large number of 8s. Instead, we should focus on identifying the breakthrough point, by applying the approximation method. That is, first look for a number close to 2005. For example, 8,888 divided by 8 plus 888 equals 1,999. This number is 6 less than 2005, so we can now transform the problem into, can the remaining 6 8s be arranged to make 6? This is easy to achieve. Here is one valid expression. Skillfully using the approximation method to find a number close to the target result allows us to focus on adjusting the remaining digits to make up the difference. Also, keep in mind the special characteristics of 0 and 1 in arithmetic, which can help when choosing operations. The difference between two identical numbers is 0. The quotient of two identical numbers, except 0, is 1. 1 multiplied by any number equals that number. 0 multiplied by any number is 0. 0 divided by any non-zero number is 0. Adding 0 to any number gives that number. Any number divided by 1 is still that number. Example 3. Fill in the digits 0, 1, 2, 3, 4, 5, and 6 into the blanks below, using each digit exactly once, to make the equation true. The problem requires forming 5 numbers using the digits 0 through 6, with each digit used exactly once. From the structure of the equation, we can see that 3 of the numbers must be single-digit numbers, and 2 must be two-digit numbers. It's clear that the product, or quotient, and the dividend are both two-digit numbers, while the two factors and the divisor are single-digit numbers. Here are some important observations. 0 cannot be used as a divisor. 0 also cannot be used as a factor, otherwise the product would be 0, and digit 0 would be repeated. 0 cannot be the ones digit of the product or quotient, for the same reason. Therefore, 0 can only be used as the ones digit of the dividend. Now consider two-digit dividends that are multiples of 10 and produce a two-digit quotient with all distinct digits. Some valid examples are 30 divided by 2 equals 15, 60 divided by 4 equals 15, 60 divided by 5 equals 12. Among these, let's check the multiplication side. If the product is 15, it must come from 3 times 5, but 5 would then be used twice, which is not allowed. That leaves 3 times 4 equals 12 equals 60 divided by 5. This solution uses all 7 digits exactly once and satisfies the equation. When solving this type of problem, it's important to analyze both the structure of the equation and the properties of the digits involved. Example 4. Fill in the digits 1 through 9 into the blanks of the two equations below. Each blank must be filled with a single digit, and no digit may be used more than once. Note, digits 7 and 9, once used, cannot be used again. The key breakthrough for this problem lies in equation 2. The left-hand side is a product of two numbers plus 9, which equals a number ending in 7. Using inverse operations, we can deduce that the ones digit of the product must be 8. Let's look at all multiplication expressions where the product ends in 8. Now eliminate those that use digits that are either repeated or already restricted. 2 times 9 and 4 times 7 are invalid because 7 and 9 are restricted. 1 times 8 plus 9 equals 17 uses 1 twice, so it also must be excluded. This leaves us with 3 viable multiplication pairs, 2 times 4, 3 times 6, and 6 times 8. Try substituting each into equation 2 and see if the remaining digits can satisfy equation 1. 2 times 4 plus 9 equals 17. Uses digits 1, 2, 4, 7, 9 remaining digits 3, 5, 6, 8. These cannot be arranged to satisfy equation 1. 3 times 6 plus 9 equals 27. Uses digits 2, 3, 6, 7, 9. Remaining digits 1, 4, 5, 8. These also cannot satisfy equation 1. 6 times 8 plus 9 equals 57. Uses digits 5, 6, 7, 8, 9 remaining digits 1, 2, 3, 4. These can form 3 times 4 equals 12. Thus, the valid solution is equation 1, 3 times 4 equals 12, equation 2, 6 times 8 plus 9 equals 57. The key to solving this problem is to analyze the units digit and work backward from there, using the specific constraints of the problem to eliminate impossible cases. Example 5. The subtraction equation below is made up of all 10 digits from 0 to 9, with no repetitions. Fill in the missing digits to complete the equation. Using the relationship between addition and subtraction, we can convert the subtraction equation into an addition equation. This approach often makes the problem easier to solve. Rewriting the original problem to an addition equation as following. The highest digit, that is the thousands place of the sum, must be 1. If the units digit addition does not generate a carryover to the tens place, then the units place can be filled with 2, 8, or 3, 9. However, with the remaining 4 digits, no arrangement can make the equation valid. Therefore, the units digit addition must produce a carryover of 1 to the tens place. The units digit of the second addend cannot be 5 or 8, because 6 plus 5 equals 11 and 6 plus 8 equals 14, both causing repeated digits. So the units digit of the second addend can only be 9, and the units digit of the sum should then be 5. This leaves the 4 unused digits 0, 2, 3, and 8. Through testing, it can be found that the tens digit of the first addend must be 2, after which the remaining blanks can be filled in sequentially. Converting a subtraction problem into an equivalent addition can greatly simplify the solving process. Identifying the most significant digit, which is the thousands place in this case, early on provides a valuable starting point for reasoning through the problem. Example 6. Fill in each blank in the long division on the right with an appropriate digit to make the equation true. Let the quotient be written as A8b, and the divisor as XYZ, so the long division layout can be expressed as following. According to the rules of long division, we can establish these equations. XYZ times A equals a 4-digit number, according to the second line. XYZ times 8 equals a 3-digit number, according to the fourth line. XYZ times B equals a 4-digit number, according to the sixth line. From the equation XYZ times 8 equals a 3-digit number, we know X equals 1. Also, from the equation XYZ times 8 equals a 3-digit number, we know that the result must be less than 1000, but since it aligns with the middle digit 8 of the quotient A8b, the first digit A must be greater than 8. Therefore A equals 9. By a similar analysis, B equals 9 as well. Hence the quotient is 989. Now consider the divisor XYZ. From the structure of the division and given calculations, XYZ times 8 equals a number beginning with 8, according to the fourth line. XYZ times 9 equals a number beginning with 1, according to the fifth line. This suggests that XYZ times 8 equals 896, and XYZ times 9 equals 1008. Trying different values, we find that XYZ equals 112, which fits perfectly with the subtraction steps shown. So the divisor is 112, and the quotient is 989. Multiplying them gives the dividend, 112 times 989 equals 110,768. Thus, here is the full long division. Careful observation of the structure of the division and identifying hidden numerical relationships is key to finding the breakthrough in solving this problem. Example 7, in the vertical multiplication on the right, the same letter always represents the same digit, and different letters represent different digits. What 4-digit number does ABCD represent? Observing the layout, we notice that the multiplier is a 4-digit number, but there are only 3 partial products. This means one of the digits in the multiplier must be 0, and the corresponding partial product is therefore all zeros and not shown. So, C equals 0, since it's the third digit of ABCD, and the third line of partial products is missing. From the line ABCD times D equals a product ends with D, we can infer that D equals 1, 5, or 6, the digits where this pattern holds true. Looking at the line AB0D times A equals a product ends in 0, and it's a 4-digit number, this implies A equals 2 and D equals 5, since 2 times 5 equals 10, and the product ends in 0. From the line 2B05 times B equals a 4-digit number beginning with EF, we find B equals 3 or 4. By testing, B equals 4 work. Try the multiplication as following. The answer is the 4-digit number ABCD is 2405. Solving multiplication puzzles involving multi-digit numbers often starts with analyzing the simpler cases of single-digit multiplication. Identifying key digits such as 0 early on can provide useful breakthroughs. Here are the practice problems for today. Thank you for watching and hope you enjoy your math today.